Welcome, everyone. My name is Brittany Todd. I'm a member of the Fabric Leadership Team. Thank you so much for joining us today for the 9th installment of our Stitching Together Innovation with Fabric Users, led by Alexandros Koufakis and Jongejans. Before we begin, I would like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note that the chat feature has been disabled, so if at any point you have a question, please type it into the Q&A box at the bottom of your screen, and we'll answer it during the Q&A session. Last, this webinar is being recorded and will be shared with all registrants. So we are joined today by our presenters. If we can go ahead and share the slide presentation, that would be great. We have two presenters today, as I mentioned before, Alexandros Koufakis and also Jongejans. Alexandros is a scientific programmer at the Complex Cyber Infrastructure Group of the University of Amsterdam. He is involved in research on microservices, federated learning, and building energy consumption prediction. He is the principal developer of the Dynamos project, a middleware for complex data sharing use cases developed by the University of Amsterdam. Jake is researching the effect of geographical policies on the training of vertical federated learning models at the Complex Cyber Infrastructure Research Group at the University of Amsterdam. His research utilizes Dynamos, which allows policies to influence where code is allowed to execute and data is allowed to go. Some of his interests are writing, ballroom dancing, playing piano, and working with functional and typed languages. I will now pass to Alexandros to start the presentation.
Hello, everyone. I'm Alexandros Koufakis. I'm a scientific programmer at the University of Amsterdam, and in particular in the Complex Cyber Infrastructure Group, or CCI. Our group's focus is, some of the focus of our group is the decentralized systems, also compliance with policies, for example, through normative reasoning, also security, data privacy, and sustainability as some other focuses of the group. So let's go through the agenda, what we're going to go through today. First of all, we're going to show a couple of use cases of federated learning. Then we're going to share some information about federated learning. Then we're going to give some information about the implementation using microservices. And finally, then we're going to describe a bit how we did it on Fabric. And then there is a demonstration and a Q&A session. So the first use case that we're going to see is the energy prediction of the consumption, the prediction of building energy consumption. So essentially, we were trying to predict how much energy one building is consuming. In order to do that, there are many factors that affect the energy consumption of a building. For example, there are the static building characteristics like the floor area, the number of windows, and so on. Then there are some sustainability features of the house, for example, if it has solar panels or insulation. Then there are some social factors like how many people inhabit in the house, and also what kind of preferences do they have. For example, if somebody likes to keep the house more warm, then they likely expend more energy in heating it. And also there are some environmental factors like the external temperature, the external humidity, and the wind, which also affect the consumption of energy by the buildings. And the reasons why we do that is can help with the adoption of renewable energy sources. Also, it can guide the sustainability renovations that have the biggest impact. For example, we can find if maybe a solar panel has the biggest impact, or insulation, or something else. And of course, it can have financial benefits. Typically, in traditional machine learning, somebody would collect all the data sets into a central server, then join the datasets, and then train the machine learning model. But in practice, in the real world, those features might be held by private companies or agents that are not willing to share the private datasets. So using federated learning, we can overcome this obstacle by training a model on distributed and private datasets without sharing the actual data, but only sharing the parameters of the model. So in this scenario, we consider three agents. One is the utility company, a building registry, and a weather station, but all of them are distributed. And specifically, the building registry has information about the buildings, like the floor, the area of the floor, and the number of floors, the number of windows. The weather station has information about the external temperature, like also the humidity. And the utility company has information about the actual consumption of the building, which is also the target variable that we're trying to predict. Okay, so this was the first use case. The second use case is about predictive maintenance for aircraft engines. The idea here is that using measurements from sensors that are mounted on the aircraft engines, we can predict when the engines might fail, but before they actually do, so that we can react proactively doing so. And this, of course, would help, of course, with the security of the air travels, making them safer. Also, could help with making the overall service better, having fewer delays, and even maybe lower the cost of the air travels. In this use case, we consider multiple airline companies and also some manufacturing company. Yeah. And the idea is that here each company has a private data set of aircraft engine sensors, a private data set, and they are willing to contribute into one single data set, not data set, a single model that is trained on the private data sets, with the hopes that the data set that is trained on all private data sets, the model that is trained on all data sets, will outperform a model that only one company could have. Again, here the companies are geographically distributed and the data sets are private. Also note here that in this scenario, each agent has the same features, but for different aircraft engines. So they share the same schema, but for different engines, different entities. While in the previous use case, the agent had complementary features, but for the same entities, which are two different types of federated learning, as we'll see in the next session by Jake.
Federated learning is a kind of machine learning that, as Alexandros already talked about, is a way where multiple companies or multiple participants are able to collaboratively train a model without sharing their raw data. The benefits of this are that data privacy is ensured, and it's possible to comply to regulations and legislations that govern how data is allowed to be used and shared. This is especially important with personal data, where we cannot share this personal data because of these legislations unless we have explicit permissions, or when we have data that companies don't want to share with other companies because it's their own private data. In federated learning, we share the model updates, so the weights and the gradients of the model instead of the data, which allows us to train a machine learning model without having to share the data instead. If we go to the next slide. we can have a look at the two different kinds of federated learning. The first one is horizontal federated learning. Participants in this case have the same kind of features. So if we have multiple companies with the same kind of data on the same entities, we can use all of this data to jointly create a machine learning model. In this case, it's very easy to train this with a lot of clients. So a lot of different clients are able to have the same feature space, and then a central orchestrator, the server, is able to work together with all of these clients without each of them having to sync up. And you can create a model with even thousands, if not millions, of clients, such as your mobile phone. But it also works when there is different companies with their private data that they want to train this on. If we go to the next slide, we can have a look at the picture in the bottom a bit better. Here we can see 3 clients at the bottom in blue, green, and pink. Each of these has their own data, but you can see all of the columns are identical in each of the clients. They each train their own local model, and they train it based on the information that they receive from the server about the model from previous iterations. So the server can communicate with client 1, give it the parameters that it needs. It will then compute its own cycle and send the parameters back to the server, and then the server can communicate with the next client, and that goes on and on. The other version is vertical federated learning. In this case, we have different data in different places. So you have a weather station that has information about the weather in a certain area, and then a building registry which has information about the size of buildings. You have a photovoltaics company that knows whether there's solar panels, and other companies that also have other data. And all of these companies can then come together and create a vertical federated learning setup where they can train with these different features about the same entities, so the same building. This, of course, requires that we align the entities, which is to say the data that the weather station has on a local area needs to be related to the address of the building that you need to get information about the building size and the insulation and the photovoltaics from the other companies. When we look at the picture up close, we see that each of the companies has its own separate data columns, but in this case, passenger ID is the same. So we have a way to align all of these entities by the passenger ID, and then each of the clients trains its own model, which you can see above the data, and they give the embeddings of their model to the server. And then the server is able to train the global model based on these embeddings and send back the gradients that are needed to do gradient descent in each of the client models. So in this case, it's very difficult to have a lot of clients because you need each of the clients to run their own cycle of machine learning and share each of the embeddings before you can continue to train the global model and give back each of the gradients. So it's a very step-by-step process instead of being able to asynchronously say this client can train, and then this client can train, and then this client can train. I believe we go back to Alexandros.
Indeed. So now let's see a couple things about the implementation that we did using microservices and dynamos. First of all, microservices is an architectural pattern that organizes the application into loosely into a set of loosely coupled services that communicates through lightweight protocols. What is important for our use case is the decentralized nature of microservices, as we thought it fits very well for federated learning and specifically for applications on Fabric. And also microservices are technology agnostic, so the implementation doesn't matter. What is important is that the communication protocols are in accordance and compatible between the microservices. Some other benefits of microservices are that they are typically faster to deploy and to develop, and also they're easier to scale up and to maintain, and they offer better for fault isolation and more robust systems. And in the context of federated learning, we can think of the architecture of one microservice, for example, having the responsibility of data pre-processing, then another microservice having the model training on a client, and then another microservice for the aggregation or the server side training. And also we can use other separate microservices for the monitoring of the federated learning pipeline. Now specifically we use the Dynamos, which stands for Dynamically Adaptive Microservice-Based Operating System, which is a data exchange system, data exchange framework developed previously by the UVA, the University of Amsterdam. So let's go through the main components of Dynamos, starting from the bottom side of the figure. First of all, the gateway, which is essentially a component that receives the external requests from the end user and then triggers the whole process. Then the evaluator is responsible for essentially evaluating the requests given a set of predefined agreements that is inputted in advance to the system. For example, one agreement might state that two agents do not agree to participate into a shared collaborative training, so they do not want to be together in a federated learning model. So in that case, the evaluator will see that and will deny their collaboration. Then the next component is the orchestrator, which generates the microservice chain that needs to be executed in order to perform the desired operations. Also, the orchestrator has some weight-based mechanism in order to select which microservice chain is the best, is the most efficient. So if there are multiple ways to execute the same thing, the orchestrator has a weight-based method that can detect which one is the best and decide to do this. So the next step, if we go up from control plane to the data plane and into the messaging and the communication components. First of all, the messaging service or messaging queue is about the communication of the components for orchestration and management reasons. In practice, it uses RabbitMQ. Also, each agent, each service, microservice has a sidecar attached to it. And the idea here is that it can decouple the actual execution and the actual functionality of the microservice with the communication. So the sidecar is responsible for the communication between the system. So the main microservice does not care essentially about the communication. And the communication between the microservices is done through the gRPC protocol, remote procedure calls. And the reason is because they are both lightweight and fast. And finally, here is a knowledge base, which holds information about agreements between the agents and some background information, and also holds information about the current states of the agents and the services that are currently running. And then we go to the top part of the figure, which is the agents, which actually execute what it is required by them. For example, for the first use case, one agent is the building registry, the second is the weather station, and the third is the utility company. Each agent can be geographically distributed, so there's no limitation in that. And in general, each agent has one persistent service, which is responsible for receiving the requests and handling internally the microservices and the execution that takes place internally within the agent. And this persistent service spins up or starts some ephemeral jobs, or ephemeral means that it starts for a short period of time and then it is terminated. So according to the microservice chain that is received, each agent starts up the microservices within their own environment, where each one of them executes what they need to do, they return the output, and then they are terminated. Although in the context of federated learning, we experimented in having them a bit more long-term to not terminate them right away in order to avoid some unnecessary startup costs. Then Jake can continue from here, I think.
Perfect. So now that we know about Dynamos, I will be talking about how I automated the deployment of DynamoOS on Fabric. But first, let's talk a bit about Fabric. So why did we want to use Fabric? The main reason I would say is it is a dedicated research infrastructure. What that means is it provides its servers, its nodes, as well as its network to researchers to run experiments and be able to test different things on a high-speed band or high network bandwidth with very powerful servers. These servers are placed in multiple locations, so there's I believe 33 sites spread across Europe, the continental US, as well as Asia in Tokyo. And with the Fabric API, we are able to really automate how we deploy everything that we want to deploy, in this case, Dynamos, from start to finish, determining where we want nodes, how big nodes should be, and automatically setting up everything through the Fabric API. So to get Dynamos to run on Fabric, we first need to get a Kubernetes cluster running. To do this, we harness the power of KubeSpray, which is a Kubernetes deployment system that allows us to define the different nodes in our Kubernetes cluster and have them interface with each of the nodes in the Fabric network that we've created. To create these nodes, we first automate the creation of the nodes, which I'll show afterwards in a demo. And we configure each of them with the necessary resources, as well as in the location that we specify. With KubeSpray, we can automatically generate a configuration that sees all of these nodes and is able to utilize the network topology that we create with the Fabric API. And this allows us to generate, in simple terms, a completely automated configuration for a Kubernetes cluster that is defined by a single configuration at the top of the file. To get all of the Fabric nodes to be able to interface with each other, even across sites. So even if we have a node in Amsterdam and a node in Tokyo and a node in Los Angeles, we expose all of the Fabric nodes to one another with the Fabric API again, which allows them to see each other over the network. With that, we can configure dynamos for Fabric by interfacing with this Kubernetes cluster. Dynamos is built on top of a Kubernetes and automatically sees this Kubernetes cluster and is able to configure itself using these nodes. We can, again, automatically configure all of the nodes that we added to the Kubernetes cluster to be exposed to dynamos, either as an agent or a third party. And these will then automatically be spun up and configured inside of dynamos. We also improved on dynamos by removing a dependency on Docker, and we're now only running on containerd, which means we have a much smaller footprint in terms of setup and deployment. And with a few other minor tweaks, the setup on Fabric is seamless, and we're able to spin up a configuration anywhere we want at any time. So if we go to the next slide, we can see a few bullet points with the main benefits that we've noticed while using Fabric as our infrastructure backbone. The first one is really the stability of dynamos. We see that it is very stable because of the very high bandwidth network backbone that Fabric has, which means that all of the messaging between nodes just works instead of having some things not work out as well or maybe fail to deliver. And the second thing, which is really important in academic research, is that we can reliably reproduce the deployments we have of our Dynamo system without having to do any manual labor. We can click a button and everything will be configured for us. And with the configuration that I just talked about, it is possible to seamlessly configure dynamos to run either on a single site or on multiple sites for an intercontinental cluster spanning 3 continents, which allows us to really test the things that dynamos can do when it is running in a distributed fashion. Now, there is a bit of future work. My research in my thesis will focus on getting this vertical federated learning to run natively in DynamoOS and utilize the policies that Dynamos brings to offer that to different companies that want to train a machine learning model together. And this research is backed and ran on the Fabric infrastructure to provide a stable basis and to allow in the future also to have research into geographical policies where certain training is only allowed to happen in certain areas of the world, be that Europe or some specific part of the United States, which is all able to be defined in a policy. I believe next up is a demo video. There is no audio, so I'll be giving a voiceover for the video. And here we can see dynamos running on Fabric. So we have two sites, the US site and the EU site. And in the US site, we have dynamos running the core. And if we go back, perfect, it's still running. And in the EU, we have these building and weather stations running. And in the US, we have the utility company again. So when we continue the video now, we can see that Dynamos is in its initial state. Everything is launched. We're having some trouble. We can just let it play. And we will be running a demo here. So we have a front end where we can request a request type to be run, and we define the aggregation node as well as the data providers. And now we can send this VFL request, and we can see that the utility company, the building registry, and the weather station are all communicating their embeddings to each other to locally train each of the models, and then jointly train the global model at the utility company, as we determined that the utility company is the aggregation node. And then it's finished, and we can see in the response that 3 rounds have been run, and we can see the accuracy of the models. Now, if we have some more time, and I just would like to get a quick indication if we do have time.
Yes, you do have time.
Perfect. We do have time, so I can actually give you a live demonstration. So here we have the configuration for our cluster. So we have the node configuration for a control node, which is run in Amsterdam. This runs the Kubernetes cluster. We have the Dynamos node, which orchestrates the entire Dynamos cluster or middleware. And we have 4 agents running. We could also make this a third party, and it would change this into a third-party instance. And each of these is configured with a set of cores. Most of them are running on 4 cores and 16 gigs of RAM. We could change this so the control node doesn't need as much in terms of cores and RAM, so it has fewer cores. And in this notebook, if we were to run it, we'd be adding the slices. So these slices are the node, are a set of nodes that we will be using to put the Kubernetes cluster on. And then we have things to do with setting up the network. And we can see here that everything is created. So we get all of our nodes that we just configured, and they are all connected through network interfaces. And throughout this automation, we define things that we need. So IP assignments will happen, and kube spray is set up here. And when we run all of this, in the end, we get to install all of the agents and all of the third parties. This is an old execution, so it still had third parties. And here we actually start up the Dynamos configuration. And what that will net us is here in K9s, we see everything working in terms of Dynamos. So we have Alpha here, we have Enigma. So these are the different nodes that we've set up on Fabric, and we have Zenith and Omnia here as well. And when we run a request, this time in my terminal, a vertical federated learning training model request, we get to see that slowly Dynamos is spinning up these new containers. So at the top, we have Alpha and Enigma spawning a new container. At the bottom, we have Zenith and Omnia. And here we see that the model training is happening. We see a lot of information being printed out, and we see that it is communicating with the training instances, which are getting a request from the server to train their model, which shows it working. And that is the live demo. So I believe I give it to Brittany now.
Yes, thank you so much. I appreciate both of you and your great presentation. Now we'll move to the Q&A session. So let's begin with just the questions that were submitted during the presentation. The first one we have is, what are the challenges with installation of Dynamos and Fabric?
Yeah, so the main issue that I've ran into getting Dynamos working on Fabric, and mainly also Kubernetes, is that Fabric has its own network and its own way of handling the network. So setting up the different configurations for the network interfaces for each of the pods in Kubernetes has its um, quirks to get it working. But after some configuration and switching to a simpler network interface for Kubernetes, things were much easier, and it was seeing the Fabric network much better. And now deployment is actually running flawlessly every single time.
Thank you so much. The second question we have is, what is the significance of the geographical distribution, and how are you planning to use it in your research?
Yeah, so the significance of geographical distribution is not every company is in the same area. And if one company is in the United States and another is in Europe, you have different policies governing their data management, both from a legal perspective as well as from a company's perspective. And if you want to move your operation in different areas, the legislation changes, and this will have an effect on how you can run different operations in terms of, for example, federated learning. And the significance here is we want to be able to determine where things are allowed to run based because of a higher up policy being set.
Excellent, thank you. The next question we have is preparation of data. Do you need to stage a lot of data for your experience? Maybe that should say experiment.
Yeah, I believe it should. They are referring to experiments. So our research is mainly utilizing synthetic data right now. It's relatively normal to use a synthetic set to be able to show that things are running according to how we would expect such a model to run. So we can compare it to other instances of vertical federated learning, for example, and see whether there is any discrepancy in accuracy. So the amount of data is not incredibly much, but it is chosen to be able to verify what we do.
Yeah, if I may add to this, for now, maybe the focus is more to develop the architecture and develop the infrastructure. And then in the future, we'll try to scale up even more. But yeah, for now, the data sets are not that big.
Awesome. Thank you so much. The next question is, with Europe having higher data privacy standards, does that inform your research at all? Yes,
it's a big thing for our group. Also, you can find more information. I think the group, the CCI link is on the chat. But yeah, definitely it's a big thing for us. So specifically, this is a big reason why I also implemented research on federated learning. With the idea is that using this, we could have more secure. We could adhere to data privacy rules and legislature, even though we use it for training a collaborative model. And also, yeah, overall in our group, there are many more directions that we focus towards for this reason, yeah.
Thank you. So another question we have is, can we please create a document with the links that we sent in the chat box and share it with all participants? So I just wanted everyone to know that we will be sending out the links to this presentation, as well as the links mentioned in the presentation afterwards to all registrants. So you will be getting that. The next question is your model training done in labeled data or unlabeled data?
Yes, in both the use cases, the data are labeled. In the first use case, where is the prediction of energy consumption of buildings. The goal is to predict the future energy consumption. So it's a forecast model, but we have labels, past labels. And the second use case, the goal is to predict an upcoming failure of aircraft engines. So we also have a labeled data set.
Awesome. Thank you. You mentioned different aircraft manufacturers. Do you actually have some of them as partners in your research group overall?
We actually have some partners, not on aircraft manufacturers, but on airlines. So we have some connections. Well, our group has some connections with this industry. So yeah, there is some collaboration. Although for the demo we didn't use any private data sets. We used only publicly available data sets. But yeah, this is something that we are examining. We're looking into.
Excellent. Thank you. And the last question, do you consider the computational energy consumption associated with federated learning? How do you address it?
Yeah, so we are looking into it. So we have someone else in our team who has already done energy efficiency research in dynamos, and we'll be able to utilize this research also to see how the implementations of federated learning behave in terms of energy usage. And this information can also, in the end, drive policy again. We have someone else who will pick up this research and utilize the energy usage of different microservice chains to also affect how these chains are created to make sure they're more efficient.
Excellent. Did you want to add something?
Yes, if that's okay. Also, yeah, another thing that we're examining, and it's for our plans for future work, is to have a mechanism to try to incorporate the energy consumption, the computational energy consumption, in the orchestration, in determining which microservices, which operations to be executed. So that's also a plan for upcoming research.
Yeah, and maybe one more thing, we are also looking at how we can reduce So startup times using persistent jobs compared to ephemeral jobs, as Alexandros also mentioned already, which should reduce startup times and having to spend energy getting the models up and running again.
Excellent. Thank you so much. And thank you again to our presenters, Alexandros and Jake. And in addition to our presenters, we would also like to acknowledge the behind the scenes teams listed here who worked diligently to bring this webinar production together. So thank you so much to these people. And also thank you to the audience for your participation in today's webinar. As I mentioned during the Q&A, that a recording of this webinar, in addition to a list of resources, will be sent to everyone who had registered for this. The slide deck will also be shared along with our Connect with Us form. So we hope you will reach out to the Fabric team for any questions or support that you may need. And our webinar next month is Mastering Fabric Tips and Tricks webinar on June 17th at 3 p.m. Eastern. And this webinar will be focused towards existing users, and we would appreciate it if you could forward the information to the relevant users in your community. As a final reminder, please submit your Fabric matrix and make sure your project description in the portal is up to date, as we will use that information for outreach, including our website. Thank you again, and have a wonderful day, everyone.